Anybody has some announcements before we start? If not, it's a pleasure to have Joe giving us a seminar again. He's going to give us a bargain here. 2 for 1. I just hope it won't last too long. So, Joe, go ahead.
Some kind of a game.
It's the same price.
Okay, the title was 2 for 1 at the same price. Did anyone figure it out?
It's the same price each.
The price applies game theory, so you're going to play a game. 2 for 1. The 2 Fibonacci numbers that are sequential, those are my 2 tops. It's just a plan. I'd like to talk to you today about 2 things. The first of these is, both of these are something very different from what we normally see in physics. And the first of these is, came about as a result of some work I did some time back that I have morphed into something that I would like to present as game theory. And it started, my thinking about this came, as you probably know, well, let me just go through my slides, and I think that'll take us down the route of history. I don't know that we... That's probably better. I don't know. Can everybody see it okay with
Yep.
half the lights? Let's do it that way. The theory of games, as you know, was laid out by von Neumann and Morgenstern in 1948. He actually did a lot of the work before that. And there's some very interesting stories about the origin of that. As you know, von Neumann was at the Institute for Advanced Study along as a permanent member along with Einstein and Hermann Weyl, who worked in group theory. John Nash did his PhD thesis when he was 22 in 1950 on non-cooperative games. And someone made the statement recently that I read that in all of the 50 years since game theory began, there have only been 2 worthwhile results. First is von Neumann's work, and the second is Nash's work. I think that's probably an oversimplification, but oops. I've got to learn to operate this mouse under these conditions. So I was at the Boston Conference on Complex Systems, and I was presenting the thing I did last spring on network theory. And I did my presentation, and their invited speaker was John Nash, which was really kind of interesting to see Nash there. We couldn't do that poorly, I'll tell you. He fell off the stage at one point. He was trying to point to something, and the stage was up here, and he stepped, but he wasn't paying attention where he went. He stepped off the stage. And at one point, he became confused, and so he had 4 typed pages. And you'll be glad to know that I will not do what he did. He read the 4 pages from the screen and stood there. If it hadn't been for the mic, we wouldn't have known because we couldn't read them from our seats. But I can tell you what he's doing. He's working with 6 PhD students at Princeton on trying to understand how you have competition in games, and that's an incredibly difficult field. And what is the structure of a game? We have players that in each round of play select from some choices that are given to them. As a result of those choices, they get some payoff. So as you know, if 2 of us decide to play a game, I may choose A, B, C, or D, and somebody else choose 1, 2, 3. And then we have a matrix between the 2. And you can imagine that matrix is going to give us the payoff that you pay me. If it's negative, then I would pay you. And of course, you try to come up with strategies and so forth. Here's an example of such a matrix. Player A is going to choose 1, 2, or 3 across the top. Player B, 1 or 2. You can say, well, look at this. This is what B pays A. B can really win here, so B will choose number 2. Well, A said, well, golly, if B chooses number 2 every time, I'm going to choose this one, then he'll have to pay me. And then B says, oh, if he's going to choose this one every time, I'm going to choose this one, he'll have to pay me some. And then A would turn that back around and say, oh, no, you have to pay me, I choose this. So obviously the only way to play this is with a strategy where you play a set of probabilities across the top and down here. And the objective of game theory, simple 2-person zero-sum game theory, which is what this is you want to be able to find out what your optimal probabilistic strategies are. What's the value of the game and what's the payoff? So you want to solve that mathematically. N players require an n-dimensional matrix, and non-zero-sum games are pretty difficult to solve, but allowances are almost overwhelming. When Nash was working on this with the 6 graduate students, I don't know how good Nash is these days, but I'm sure these 6 Princeton students in mathematics are pretty good, and they were using Mathematica, and they're trying to find optimal saddle points and these things when you have coalitions, and when can you have coalitions, And they're only studying 3 players, where 2 of them form an alliance against the third one. And we just look at table after table of maximum and minima and attempts to find it and functions that went berserk and so forth. It's very, very difficult. So these non-zero-sum games are difficult. Alliances presents overwhelming obstacles. The structure is very difficult to apply in actual practice. So when you go out there in the marketplace or in the military environment or other places like this, you try to apply this, putting the information that you have in a matrix is very difficult. And so what I've got here is I'm just going to suggest a new approach. That's why we have friends that we bring together and give talks to, so that they can help us before we go out in the world and make fools of ourselves. And so maybe someone will have suggestions for me. One still in this system is going to have players, and they're going to compete by making choices and having payoffs. So in that sense, it's still a game. But it's going to more easily encompass in-person, non-zero sum, and certainly games with alliances. And so it will allow this. And it's a different structure altogether. I'm going to suggest also that it has greater ease of applicability with real-world problems, and you can apply it immediately. It will build on known things, and so I'm not saying that the foundations that I'm building on are things that I did. I only just put them together in this way that I think is interesting. I want you to imagine that there are 4 types of players, and each of these players makes a response to a computer environment. So these players can go onto a computer, and all they do is they respond to questions. And the first group is called the creator. And he finds money, and he proportions this money out because he wants to pay people to get knowledge. He sets the game knowledge domain. That might be some place in organic chemistry. For example, maybe glues and adhesives that are applied under heat in industrial settings. Some kind of narrow intellectual domain. And he fixes that domain, and he sets certain game parameters. So he fixes the structure of the game by filling out a little sheet. From then on, the next set of people answers the question, what is your next question in this field? Now the first person, who is the creator, could invent some questions, and he may do that, but more likely he would ask other people to come in and ask pertinent questions. Then after those people pose the questions, they'd say, what is your next question? What is your next question? They just type the question in, and that's their response. Then, thirdly, next down here, you have a group of people that value those questions. I mean, some questions can be valued very highly. What's the mass of the proton? It's extremely important. What is the Dow Jones going to do in 1 year? Incredibly important. Can we win this war with an expenditure of only $1 billion? Very important question in the time frame of 1 year. Then the final group answers each of the questions. And say, well, this is just like giving an exam. Not exactly. The question, there are certain rules to this, and the questions are to have one-word string responses, word or number, that's unique and unambiguous. That's the first rule. So we have to have answers that are computer comparable. The questions can't be too difficult or trivial, because if they are, that doesn't add anything to the game. The players have a window of time, so you can come on, you can play this game over the internet, and you have a window of time to respond, and you'll respond electronically without the knowledge of the other players. The questions are restricted to a fixed knowledge domain, and the reason for that is you want to estimate probabilities that these people are going to be correct and look at the overlaps of those probabilities. And that's only going to be valid within a certain knowledge domain, like organic chemistry or intermediate energy particle physics or anatomy or something like that. There must be enough players to statistically overlap, thereby estimate the probability that an answer is correct, and enough questions to estimate the probability of each person's correctness. So in what follows, P sub I is the probability that person I is correct in that domain of knowledge. And E alpha mu is the probability, the expected probability that for question alpha, the muth response is going to be correct. Okay? So we can take all the responses that come in and we say, oh, these are equivalent within spelling, alphabetically sort them, so you've got 7 responses, and so we're just going to number those responses. Mu is equal to 1 to 7. The game creator decides how to partition the payoff among the groups, although there is another way to do that, I won't go into it. But within a group, you use Shannon information to partition how the payoff is done among the people. For example, the people who are doing the rating or the people who are answering the questions. The players register online, so now you get ready to play the game. So you go onto the internet, you're going to register, and you provide an email address, and you give your name, and you get back over your email address a PIN number and a password. Now you take that, and all of the people who will play will use that PIN number. And they'll have certain restrictions on them. The creator of a game could say, I won't let you in this game except if your PIN number is here. You have to answer certain questions correctly or something like that. It might be qualification tests like we have to get into the university for the people to participate. The system will run on its own from that point. A creator goes and gets money, picks a domain like organic chemistry, intermediate energy particle physics. He puts it in. He may ask some questions. He may just turn it over. Another group begins asking questions. Another group begins valuing those questions. A final group begins answering the questions that are there. The system is self-sufficient, and it turns out that this is a system of coupled to nonlinear equations. You can see that this is true because if you start out, the probability that a person is going to be correct, if we just grade them, it's going to be the probability. If we know what the answers are to the questions, then we just grade the test, so to speak. We would know that the probability is 1 for the right answer and 0 for the wrong answer. But in general, we're not going to know that because we can't, everyone is just a student. Someone can say, well, I know what it is. You could put that in by default, but that's not what we do. That's not the way it's played. So you have a certain probability that mu is correct for alpha. And epsilon I alpha mu is the choice that person I makes for question alpha, and he chooses mu, then that epsilon I alpha mu is going to be 1, otherwise it's going to be 0. So epsilon I alpha mu is going to be a three-dimensional structure of just 1s and 0s, and it shows who chooses, which person chooses, which, for each question, which answer. And it puts a 1 there, it's a 0 otherwise. All the information in the game is really contained here. Likewise, the probability that a particular answer is correct depends upon the probability of the people. So the probability that the answer depends upon the overlap of the people. The probability of the people depends upon the probability of the answer. And you couple these two systems together. I don't want to spend a lot of time on equations, but you could guess that this first equation up here is where you're basically grading the responses. If I know E alpha mu, and that this is a laser, isn't it?
There's one down there on the table that's better.
No, thanks. This is probably does something evil to. If I look at this, I can say, if I know the right answers, these are just 1s and 0s for the right answers, and it grades them based upon who chose what, and so this is just grading the test, and I divide by normalization. Down here, I can say, what are the probability of the people? Well, I've got a value there. I really expanded this now, and I'm saying, well, if this is only an estimate, the epsilon alpha mu, then I want the best estimate to be greater than 50%. If I don't have an estimate greater than 50%, you could put in another step function there, but I think one answer should be more valid than the collection of the rest of them. That's what I did here. I just put this theta function in. I also put a value for question alpha, because we're going to have a way to value each question, so some questions count more than others. And so you get more credit for it, and you put your normalization there. That gives you your probability that you're correct in that domain of knowledge. Now let me give you an example of how you estimate the probabilities of the responses. Let's suppose for question 8 that answer 1 is answered by person 1, 2, and 3. And person 4 and 5 don't choose that response. Person 2, for answer response 2, that's not chosen by 1, 2, and 3, but it is chosen by 4 and 5. So the probability that this question, that this answer is correct, number 1, is this probability times this one times 1, the probability that this guy is wrong and this guy is wrong. Likewise, the first 3 guys are wrong here and these other 2 here. And there's a normalization here that normalizes those 2. And what's interesting is you can kind of take these structures, and if you take that, you can rewrite it in the following way. I can multiply the whole equation by 1 minus P1, 1 minus P2, and so forth, and put it in this form right here. And you can see that epsilon being only 1 and 0, if it's a 1, it chooses this factor right here, and this cancels this, so you get P1. If it's 0, this doesn't appear, and I get 1 minus P1. So it's kind of neat. And so this equation right here gives us our E's, our E probabilities in a better way. I define Ri to be the logs of the probabilities, which really is the difference of 2 Shannon entropies, the log of the probability to be correct minus the log of probability to be wrong. And that's basically a log of the odds, which is kind of interesting. This RI is very important here, and I can now recast this, putting this up here, bringing this down here, taking the logarithms and exponentiating it. There's this simple sum where these are Rene, these are Shannon entropies here. The payoff to a person who correctly answers is going to be proportional to what their Shannon entropy is and the value of the question, summed over those questions to which they responded correctly. So you have now by correctly, we don't know what the answers are. So the system is figuring out what the answers are. And it solves all these systems iteratively, back and forth between the probabilities and the people. Yeah?
May I ask a question? This third and fourth formula assume that all probabilities are independent. Therefore,
Yes, it does.
but usually if you ask some question for real person, they have common background, common education.
In fact, if they didn't have any common reality, they couldn't overlap. So that is a valid point. We're assuming that they're independent in the sense that this will work. Now, I've actually tried this. If you bring people together and you ask them questions like, what is the name of this river? You want them to know the name of the river from some common educational environment, so the probabilities are connected. But it's that overlap that precisely gives you the fact that you can estimate that probability. But his question is, the dependence of the probabilities is an issue here, but we assume that we can ignore that, which Vladimir doesn't like on that. Questions can be given a value. Now we're going to do some refinements. And we can say that the value of a question is, we have a whole bunch of people, J people, valuing the alpha question. And each person, each of those J people, have a certain weight, how good they are at evaluation. And now we come down here, and so all these people start them out as equal, so they all have the same democratic ability to vote. And so then they go in and they vote on these questions, and then we get values. But some of the people, exactly like in experimental physics, are going to be outliers. They're very far from the norm, and you assume that the norm is correct. So the further they are from the norm, you say, well, these people aren't very good at valuing questions because the norm is going to be correct for these people. So we take the weights and alter the weights depending upon how many standard deviations they are, actually the information for the overlap of the Gaussians, how far they are out here in some distance. And then we get a new weight. We take the new weight and go back in and compute a new value. Using the new values, we get a new mean, go back and compute a new weight. So this to this, and I didn't write the equations down for this, become another coupled system of nonlinear equations. And the mathematical basis for the game is entirely contained in these numbers, the epsilons, of which choice is 1 for the alpha question for the ith person. And so it's just ones and zeros. And these numbers, which are values. So everything else is contained in that set of numbers. So now one can look at these 4 sets of coupled nonlinear equations and say, what is optimal? How many questions should be answered if the probabilities of this? So there are all kinds of mathematical questions we could raise. We are constructing another web portal in addition to one I described that would allow one to go in and do a simulation, picking a range of people that have certain probabilities, letting them respond, let the computer not know which is the correct answer. Of course, it would go through and it would grade, it would estimate the answer, even though it would know in the background which is the right one. Let the system generate how many people are correct, how many people you need, how many questions you need, how reliable, hard the questions have to be, and you make a whole series of curves, and you can do that. This whole domain of knowledge is known in the business world and in several other areas as expert opinion, overlap of expert opinion. I didn't invent this. I just used there are tons of different models for it. I chose this one. The creator for the game can choose a slightly different way that he constructs it, and so that's not that important. And so we intend to couple that with something like our DARPA intrusion, which means what would this game do? Well, the game, for one thing, would be able to sit there and you would look at the internet. You'd have models over here that would say, we have an intrusion here. And you'd have 2 people who are experts, and one of those experts would say, I think that that's an attack. The other guy said, no, I think a server's down. And the computer and the 2 people could all vote. They could even form a coalition and vote collectively. And so you get all kinds of new types of structures. It's much more robust with N players. It doesn't care whether they're non-zero payoffs, and it embraces allowances. Specifically, alliance can be not just a group of players, as I was explaining, but not just a group of players playing a subgame, but some of the players should be computers, and some of the players can be experimental equipment. So, for example, I can have an apparatus over here. Maybe I'm trying to measure the mass of the proton. Well, that's not very exciting. Let's imagine we're measuring the mass of the neutrino. So we've got some apparatus, and it spews out this measurement, and then takes data for another year, and it spews out another one. Another guy over here is modeling it in some terms of some computer model. He comes out with answers based on some data and some simulations and things that he thinks. And somebody else has another simulation. Guy's an expert. He looks at it and he said, no, I don't think this data is quite right here. Because of the tail here, I think it's probably shifted to the right. He can put in a vote. They can collectively, the experimental apparatus, the computer model, 5 computer models, and 3 people can all collect, just like a team does when Dr. Rosenfeld goes out. They all get together and they say, there is a mass here, there is a resonance, there is a particle, no there's not. And you can vote and say, we've gained information there. And of course their money is coming from the NSF or the Department of Energy, and that's the creator of this game. Here's an example. You have 2 meteorologists, 3 computer models, and they make weather prediction, and there's a subgame there. And you want to know whether you want to watch the weather on WIS or you want to go to the Weather Channel. And so basically, this system keeps track of all the probabilities of the people, both within the subgroups and how they vote and how good they are. And here you have another player, Weather Reality, that you can bring back in later. And Reality can vote 5 days later and say, it did not rain and you said it would. And that player is correct with 0.9999% accuracy. And so it corrects all the probabilities and so forth, as depending upon how close they came to it.
Before something happens, you have probability. After it happened, it is not probability at all. So how is it?
No, it's not certainty either, because there's some possibility that this apparatus that said it rained there, really somebody spilled a drink and it splattered into the apparatus. It's always some probability this is incorrect. But if you want to say it's certain, you can say it's certain, and then that'll work fine too. It goes in and it corrects or adjusts those probable players. But you can't let reality play. Otherwise, if reality were playing, you just go look and see if it's raining. And that's not very interesting. This game is to say, will it rain in 4 days? What will the Dow Jones be in 1 year? What will IBM stock be? And here's some examples.
But after the fact, after this time passed, you say that you readjust. You just
Yeah, you can adjust after the
in this
fact,
particular
but it
way.
also adjusts as you go along. What will the Dow Jones be in 1 year? Well, actually, you can make that a whole bunch of questions. You take the Dow Jones and put it in binary form, and everybody in this room could get the first 12 digits probably of the binary form of the Dow Jones average in a year from now. That's a huge number. I mean, it's, what is it, 12,000 now or something like that?
11,000.
11,000, getting close to 12.
Yeah.
Okay, say it's 11,000, huh?
Yeah.
Let's be optimistic. It's about 12,000, getting right close to it. So, I mean, we've got a whole bunch of numbers that everybody agrees on. Then there are a bunch of numbers that are going to be real fuzzy. Well, I think it'll go up by this amount. So you start getting into a bunch of digits that people disagree on. And the further you get along with the binary digits, yes, no, you get more and more chaotic until finally, you know, out here in the 15th decimal place, nobody even knows what the Dow Jones Industrial Average is when you measure it like that. So it has no absolute meaning. So I can imagine the 3 different domains. Those where everybody agrees and is not very interesting. Those for which there's some voting and kind of agreement among the experts and so forth. Do the same thing with the next 5 binary digits in the mass of the proton.
So the ultimate goal is to find out how good a guesser is, or a combination of guessers to
Yeah,
find the
it's
best.
a combination of the abilities of the people in the subgroups using equipment or models or whatever. They come in and they vote, and then the system assumes that the collection of the whole is probably the most valid answer, goes back and corrects people for that, gives them a payoff based on that, continues to cross-correlate, making constant corrections.
So you'll sort of be optimizing your team of people plus computers to...
Yeah, and that's what, then that becomes a mathematical problem. How do you choose, if you were to know the probabilities in the different areas, how would you choose the people so that they would form sub-teams that would be unbeatable? And of course, what you get paid for is the information that you bring to bear in a particular question. So every time there's a question, you look at the value. The value is partitioned by the dollars that you were given, by the investor, the creator, the NSF, the DOD, whatever it is to find this out. There's some interesting questions. What will be the score for an athletic event? After the fact, it's not very interesting. Before it, it's quite a bit of interest. There's a lot of money right there. Believe it or not, it's illegal. But you know, who's going to win the World Cup soccer a year from now? People can estimate, you know, which country might win. And the more you know about individual players, and the more you know about where it's going to be played, and what the weather's going to be, and what the condition is of that field, you begin to know more and more, and you begin to converge among those experts. And the people who are just guessing randomly, they're spread out.
So in
And
other
so-
words, you, in your game or sub-games, you allow complete ignorance as well as those who are informed.
You missed the
So-
first sentence.
I know.
When we started, the creator can have a selection process. So
Oh yeah, so
like you have to have
selected,
you have to have an MD degree to decide whether we're going, how we're going to take out this guy's appendix. Or, I mean, you don't want just people off the street. What's the best surgical procedure? What's the cost in man and materials needed for this military conflict, and with what probability does one achieve what gain?
Even if the answer is given, they will not listen to you anyway.
It's not, listen to me. It's, the whole idea is that the system is autonomous and it would run by itself. So it would sit there like an engine. So we can build a software engine, and we're building it now. And, I've done it before.
The deciders don't pay attention what experts say. This is the rule of the game.
I'm not going to worry about that. There are people, there are people who have a lot of money who would like to bring together people with great investment knowledge. And they could even choose the people that would participate in the game. And there's an advantage, because what you know is nobody knows what these probabilities are. So when you play the game, you just enter your bank account, and the money appears when you're right. And at some point, when there's not much money there and you're spending a lot of time, it's not worth it for you to play, and so you quit. You're not competent compared to the rest of the people. And the people who can enter the game gain their probabilities, and after they have a certain probability, they go on with that.
I think his comment only applies to political decisions.
I mentioned the last point, of course. Whatever the experts
Oh, in
say.
case you're curious, that is what the curve looks like for the log of the probability divided by 1 minus the probability. You'll notice that it really shoots up. In fact, when you get to 0.9999% right, you're worth 16 people at 0.75. I think that's about, I may not be showing it on here correctly. The graph didn't go quite that high number of people. But you can see that one person who is about 85 is worth 2 people at about 73 or something like that. So it's a very interesting nonlinear relationship, and you're going to get money based on that probability. And it's actually the log of the probability divided by 1 minus the probability. And there's probably some name for that. Where's Rick? Sorry. Rick, is there a name for the log of the odds? Never heard of that. Anyway, that's the natural thing, and that's used for the payoff. Thank you.
A surprise.
Hey, I did it.
What? What?